Throughout history, science has been built on a foundation of principles, laws that govern the motion of planets, the behavior of atoms, and the very structure of reality. These laws are tested, refined, and trusted because they allow us to make predictions with extraordinary accuracy. But what happens when two of the most fundamental laws of nature come into direct conflict? This is exactly what the Blackhole Information Paradox represents. A deep contradiction between the two most successful theories in physics, general relativity and quantum mechanics. One of them tells us that information can be lost forever, while the other insists that information must always be preserved. Both theories have been confirmed by countless experiments, yet when we apply them to black holes, they clash in a way that shakes the very foundations of our understanding of the universe. At the heart of this paradox is a simple but disturbing question. What happens to information that falls into a black hole? To understand why this is a problem, let's consider a simple example. Imagine you take a drop of ink and place it in a glass of water. Initially, the ink is concentrated in a single spot, and you can clearly see its deep color. But as time passes, the ink spreads out, diffusing into the water. Eventually, the entire glass takes on a light tint, and the original drop is no longer distinguishable. At first glance, it might seem like the ink drop has disappeared. But has it really? According to the laws of physics, the answer is no. Even though the ink is now evenly distributed throughout the water, the information about where the ink started still exists. In principle, if we had a powerful enough understanding of molecular motion, we could track every particle and reverse the process, reconstructing the ink drop's original state. The system has become more chaotic, but the fundamental information is still present. It hasn't been erased. Now, let's change the experiment. Instead of dropping the ink into water, imagine dropping it into a black hole. Unlike in the water, where the ink spreads but still retains its information, the black hole swallows it entirely. From the outside, it appears as if the ink simply ceases to exist. For a long time, scientists assumed that while the ink drop or any other object vanished beyond the event horizon, its information must still exist somewhere inside the black hole. Perhaps it was stored on the event horizon itself, or perhaps it remained trapped deep inside the singularity. But then came Stephen Hawking's discovery in 1974, which changed everything. Hawking showed that black holes are not truly black. Instead, due to quantum effects, they slowly emit a faint radiation, now known as Hawking radiation. Over time, this radiation causes the black hole to shrink and eventually disappear completely. Here's the problem. Hawking radiation is completely random. It carries no information about what fell into the black hole. If the black hole evaporates entirely and all that remains is this random radiation, then the information about the ink drop, its exact structure, its original position, would be lost forever. This directly contradicts quantum mechanics, which states that information can never be destroyed. Thus, we are left with a paradox. General relativity tells us that once something falls into a black hole, it is gone forever. Quantum mechanics tells us that information can never be lost. Both theories have been tested and confirmed in different areas of physics, but when applied to black holes, they contradict each other in a way that suggests our understanding of the universe is incomplete. Why this paradox matters? At first glance, this might seem like a problem that only affects extreme cosmic objects like black holes. But in reality, this paradox challenges the very foundation of physics. Every time a paradox has appeared in the history of science, it has led to revolutionary discoveries. The conflicts between classical physics and electromagnetism gave rise to Einstein's theory of relativity. The contradictions in early atomic models led to the birth of quantum mechanics. The black hole information paradox could be pointing us toward a deeper theory, one that unifies quantum mechanics and gravity into a single, all-encompassing framework. Many scientists believe that solving this paradox will lead us to a theory of quantum gravity, the missing link in our understanding of nature. Chapter 1: The Birth of the Paradox. What are black holes? To understand the paradox, we first need to understand black holes. These are some of the strangest objects in the universe, so strange that for a long time even scientists didn't believe they could exist. A black hole is formed when a massive star collapses under its own gravity. If the star is big enough, no known force in the universe can stop this collapse. The result is an object with an incredibly strong gravitational pull, so strong that nothing, not even light, can escape. This is why black holes are black. They don't reflect or emit light. The boundary around a black hole, beyond which nothing can escape, is called the event horizon. Anything that crosses this invisible boundary is lost to the universe forever. At the center of the black hole lies a point of infinite density called a singularity, where all the mass of the black hole is concentrated. The laws of physics as we know them break down at this point, making it one of the greatest unknowns in science. The discovery of Hawking radiation. For a long time, physicists believed that black holes were completely inescapable prisons for anything that fell in. But in 1974, Stephen Hawking made a groundbreaking discovery. Black holes are not entirely black. They actually emit tiny amounts of radiation, now known as Hawking radiation. This happens because of quantum mechanics, the theory that describes particles at the smallest scales. In empty space, pairs of tiny particles and antiparticles are constantly appearing and disappearing. Normally they cancel each other out, leaving no trace. But near the event horizon of a black hole, one particle can fall in while the other escapes. The escaping particle carries away a tiny bit of energy, making the black hole lose mass. Over time, this process causes the black hole to shrink and eventually disappear completely. But the question is, where does the information go? Here's where the paradox begins. In physics, information is never truly lost. If you burn a book, the information is scrambled but still technically recoverable. But if something falls into a black hole and the black hole eventually evaporates, where does that information go? There are only a few possible answers, and all of them lead to deep problems in physics. 1. The information is truly lost forever. This would mean that the fundamental laws of quantum mechanics, one of the most well-tested theories ever, are wrong. 2. The information escapes with the Hawking radiation. But Hawking's calculations showed that the radiation carries no information. It is just random heat energy. 3. The information is stored somewhere in the black hole and released at the very end. But this would require new physics beyond our current understanding. This paradox is not just a curiosity, it strikes at the heart of how the universe works. If information can be lost, it would force us to rethink everything we know about physics, from the smallest particles to the structure of space and time itself. With this foundation set, we now dive deeper into the theories and ideas that have been proposed to resolve this puzzle. Chapter 2: Theoretical Foundations. To truly understand the black hole information paradox, we need to explore the two pillars of modern physics that are at odds: general relativity, which describes gravity, and quantum mechanics, which governs the behavior of particles on the smallest scales. Each of these theories has been tested extensively and has proven to be extremely accurate. But when they meet at the edge of a black hole, they seem to contradict each other in a fundamental way. The laws of quantum mechanics. Why information must be preserved. In the world of quantum mechanics, information is never truly lost. This idea is tied to a concept called unitarity, which means that if we know the state of a system at one point in time, we should be able to determine both its past and its future. To put it simply, if you have a movie of a quantum process and play it in reverse, the physics should still make sense. Every interaction between particles follows strict mathematical rules, ensuring that no information is destroyed. Even if a system appears to change completely, in theory, the information about its previous state is still embedded somewhere. For example, imagine you have a glass of water and you drop a piece of ink into it. At first, the ink forms a neat drop, but over time, it spreads and mixes, making it impossible to see the original droplet. However, If you had an incredibly precise understanding of every molecule's motion, you could, in theory, reverse the process and reconstruct the original droplet. This principle applies to everything in quantum mechanics. No matter how complex a system gets, its initial information can always be traced. If a process completely erased information, it would break the fundamental laws of quantum physics. Now, let's turn to black holes. When something falls into a black hole, we lose all knowledge of its physical state. Whether it was a book, a spaceship, or a cloud of gas, once it crosses the event horizon, all we know is that the black hole's total mass, charge, and spin might change slightly. But every other detail about what fell in is gone. If Hawking radiation causes the black hole to evaporate completely without carrying that information back out, then the original information is lost forever. According to quantum mechanics, this should not be possible. Information cannot just vanish. Yet, according to general relativity, black holes allow precisely this kind of information loss. General relativity, the one-way trap of black holes. On the other side of the paradox is Einstein's theory of general relativity, which describes how gravity works on a large scale. In this theory, black holes are natural consequences of extreme gravitational collapse. They warp space-time so severely that once something falls in, it cannot escape. General relativity treats black holes as smooth, featureless objects. This is sometimes called the no-hair theorem, which means that black holes have only three basic properties. 1. Mass, how much stuff is inside. 2. Charge, if the black hole has an electric charge. 3. Spin, how fast the black hole is rotating. Beyond these three properties, nothing else about what fell into the black hole matters. If you throw a diamond or a pile of trash into a black hole, the final result is the same, a slightly more massive black hole. There's no way to recover the original details from the outside. This is where the problem deepens. If a black hole eventually evaporates, leaving behind only empty space, then according to general relativity, the information about everything that fell in is completely gone. General relativity does not have any built-in mechanism to preserve this information or recover it later. But quantum mechanics says this is impossible. Information cannot simply be erased from the universe. So who is right, general relativity or quantum mechanics? The conflict between two fundamental principles. The black hole information paradox exists because these two theories, both of which work incredibly well in their own domains, predict completely different things when it comes to black holes. Quantum mechanics demands that information be preserved, no matter what. General relativity allows black holes to erase information permanently. This contradiction means that at least one of these two fundamental theories must be incomplete. Either we need to modify general relativity to allow for information preservation, or we need to change quantum mechanics to allow for true information loss, something that has never been observed anywhere else in nature. The paradox is so severe that it suggests we may be missing an entirely new aspect of physics, something beyond both quantum mechanics and general relativity. In other words, solving this paradox might lead us to a deeper understanding of the universe, possibly even a theory of quantum gravity that unifies these two great frameworks. The thermodynamics of black holes. A clue? One major breakthrough in our understanding of black holes came when scientists began treating them like thermodynamic objects. Thermodynamics is the branch of physics that deals with heat, energy, and entropy. Entropy is a measure of disorder, how much information is lost in a system. The second law of thermodynamics states that entropy always increases. For example, if you smash a vase into pieces, you increase the disorder of the system, making it much harder to reconstruct the vase. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking realized that black holes must have entropy. The reason is simple. If a black hole absorbs matter and energy, and that matter carried entropy, the total entropy of the universe must still increase. Otherwise, the second law of thermodynamics would be violated. Hawking's calculations showed that black holes do, in fact, have entropy, and this entropy is proportional to the area of the event horizon. The larger the event horizon, the more entropy the black hole contains. This was a surprising discovery because it suggested that even though we cannot see what's inside a black hole, its surface area encodes information in some way. But here's where the puzzle becomes even deeper. If entropy represents information, and black holes store information in their surface area, how is that information released when the black hole evaporates? Hawking's original calculations suggested that the radiation coming from the black hole was completely random, containing no information about what originally fell in. But if this were true, it would mean that information truly disappears, a violation of quantum mechanics. The more physicists thought about this, the weirder the paradox became. If information is lost, it means we would have to fundamentally rewrite the laws of physics. But if information is preserved, then something must be happening to store or release that information in a way we don't yet understand. Physicists have proposed many ideas over the years to solve this problem, but none of them are fully accepted yet. Some of the most interesting proposals include the holographic principle, the idea that all the information in a black hole is stored on its event horizon and somehow encoded in the outgoing radiation. The firewall hypothesis, a controversial idea that suggests an invisible wall of fire burns up anything that crosses the event horizon, possibly affecting how information escapes. Wormholes and baby universes. Some theories suggest that black holes might not destroy information, but instead send it into another part of the universe, or even another universe entirely. Each of these proposals has deep implications, not just for black holes, but for our understanding of space, time, and reality itself. Chapter 3: Hawking's Argument and its Consequences. In 1976, Stephen Hawking made a startling claim. Black holes destroy information permanently. This was not a casual suggestion. It was a fundamental challenge to everything we thought we knew about the laws of physics. Hawking's argument was based on his groundbreaking discovery of black hole radiation, now known as Hawking radiation. This process causes black holes to slowly lose mass and eventually disappear. But if the black hole completely vanishes, what happens to the information about everything that fell into it? According to Hawking's calculations, this information is simply lost. This idea was shocking because it suggested that quantum mechanics, the most successful theory of small-scale physics, was wrong in one of its most fundamental principles, the preservation of information. If Hawking was correct, it meant that black holes were not just objects that absorbed matter. They were also ultimate erasers of reality, violating the very rules that govern how the universe works. The consequences of this claim were staggering. If black holes could erase information, it would mean that the future of the universe could not be predicted with certainty. It would mean that the laws of quantum mechanics were incomplete. It would mean that physics itself, as we understood it, needed to be rewritten. But how did Hawking reach his conclusion? Hawking's key insight came when he applied quantum mechanics to the space just outside a black hole's event horizon. There, pairs of virtual particles are constantly appearing and disappearing due to quantum fluctuations. Normally, these particles annihilate each other almost instantly. But near the event horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes part of Hawking radiation, which slowly carries away the black hole's mass. At first, this discovery seemed like a huge breakthrough. It showed that black holes weren't completely black. They actually emitted radiation and could eventually evaporate. But then Hawking realized a problem. The radiation escaping from the black hole appeared to be completely random. It contained no information about what had fallen into the black hole. If this was true, then when the black hole finally evaporated, all the information about what fell into it, whether it was a planet, a spaceship, or a single photon, would be gone forever. It would be as if that information had never existed. The deepest violation of quantum theory. Hawking's claim sent shockwaves through the physics community because it directly contradicted the principle of unitarity in quantum mechanics. Unitarity means that information about a system's past must always be preserved in its future. Even if something is transformed in a complex way, the original information must still exist in some form. If information were truly lost in black holes, it would mean that the fundamental laws of physics had a loophole, a place where information simply ceased to exist. This was not just an academic problem. If information could be destroyed, it would mean that the universe was fundamentally unpredictable. Imagine a library where books randomly disappear without a trace. Not only would you lose the books, but you would also lose any record that they ever existed. If black holes could erase information, then in a very real sense, the universe would become a less knowable place. Hawking's argument was so compelling that, for years, most physicists believed him. The Blackhole Information Paradox became one of the greatest mysteries in theoretical physics. Either 1. Hawking was right, and black holes really do destroy information, which would mean that quantum mechanics needs to be rewritten. 2. Hawking was wrong, and somehow black holes must preserve information, but no one could figure out how. For decades, no one could resolve this dilemma. The paradox became so famous that it was considered a key test for any future theory of quantum gravity, the missing theory that would unify quantum mechanics and general relativity. The implications for the nature of reality. If black holes destroy information, it means that time itself behaves differently inside black holes than in the rest of the universe. In our everyday experience, events in the past determine the future. If we know the conditions of a system now, we can, at least in theory, trace back its history or predict its future. But if information is lost in black holes, then there are some events in the universe that have no past and no future, just a void of lost knowledge. This would mean that the fundamental laws of physics are not universal. They break down in the presence of black holes. It would also mean that cause and effect, one of the most basic principles of science, is not absolute. But there was an even bigger issue. If information can be lost in black holes, then why should black holes be the only exception? What stops other extreme physical processes from erasing information as well? If information loss is possible, it might not be limited to black holes. It could happen in other unknown ways throughout the universe. The challenge to Hawking's idea. Despite the power of Hawking's argument, many physicists refused to accept that information could be destroyed. The reason was simple. No other experiment in physics had ever shown a violation of unitarity. If Hawking's claim was true, it would mean rewriting quantum mechanics, a theory that had been experimentally confirmed in every other setting. Instead of accepting this drastic conclusion, many physicists began searching for possible ways in which information could escape from a black hole, despite Hawking's original calculations. Over the years, several alternative explanations were proposed. The information is stored in a hidden way on the event horizon, black hole complementarity. The information escapes in a highly scrambled form through Hawking radiation. The information is preserved in some new, unknown way that requires a deeper theory of quantum gravity. But for decades, none of these ideas had strong evidence, and the paradox remained unresolved. Hawking's own reversal. In the early 2000s, after years of debate and new theoretical developments, Hawking surprised the physics community by changing his mind. He admitted that black holes probably do not destroy information after all. Instead, he suggested that information somehow escapes, but in a way that is incredibly difficult to reconstruct. This was a major shift, but it still left many unanswered questions. How exactly does information escape? What mechanism allows it to be preserved? Do black holes store information on their surfaces, or does it leak out gradually? These questions remain at the heart of modern physics, and even today, researchers are still searching for definitive answers. The next steps in the search for a solution. Hawking's argument sparked one of the greatest intellectual battles in modern physics. It forced scientists to reconsider the nature of space, time, and reality itself. While new ideas have emerged, no single solution has been universally accepted. Chapter 4. The firewall paradox, a violent solution? The firewall hypothesis is one of the most controversial and radical ideas proposed to resolve the black hole information paradox. It emerged in the early 2010s, primarily through the work of physicists, and quickly became a key point of debate in theoretical physics. At its core, the firewall hypothesis suggests that the event horizon of a black hole is not the smooth, featureless boundary that Einstein's general relativity predicted. Instead, it proposes a dramatic and violent revision of what happens to anything that crosses the event horizon. To understand this idea fully, let's first break down what a firewall is and why it was introduced in the first place. The basics of the firewall hypothesis. The basic premise of the firewall hypothesis is simple yet shocking. There is a wall of fire at the event horizon of a black hole. This firewall is not a physical wall, but a boundary of extremely high energy that destroys anything that crosses it, including information. If this hypothesis is true, then the information about any object or particle falling into a black hole is completely obliterated at the event horizon, and it is not preserved in any way. This idea directly challenges the no-hair theorem and the smooth nature of the event horizon, which have long been fundamental aspects of black hole physics. According to general relativity, nothing special happens when you cross the event horizon. From the perspective of someone falling in, the experience should be uneventful, aside from the intense gravity. The event horizon is just a point where gravity becomes so strong that nothing can escape, not even light. However, the firewall hypothesis suggests that things are much more extreme than this. Instead of a gentle crossing, the event horizon becomes a firewall that incinerates anything attempting to enter, instantly destroying all information about the object that crosses it. The motivation behind the firewall idea. The firewall hypothesis emerged from a series of arguments regarding the black hole information paradox. Recall that Hawking's original discovery of black hole evaporation and his suggestion that information is lost forever set the stage for a significant problem in physics. If Hawking's claim about information loss is true, it violates the principle of unitarity in quantum mechanics, which states that information about a system must always be preserved. In response, many scientists spent years trying to resolve the paradox without completely abandoning the principles of quantum mechanics. Some proposed that the information is somehow preserved on the surface of the black hole or released in a highly scrambled form through Hawking radiation. However, these ideas were not without their own set of problems. The breakthrough came when a group of physicists took a closer look at the so-called black hole complementarity and the ADS-CFT correspondence, a powerful mathematical tool in string theory that relates gravity in a higher dimensional spacetime to quantum field theory. This correspondence suggests that the physics inside a black hole might be equivalent to a theory that doesn't involve gravity at all, and it pointed toward a radical solution: the idea of a firewall at the event horizon. The reasoning behind this is based on an apparent contradiction between quantum mechanics and the smooth, featureless nature of the event horizon. If quantum information is supposed to be preserved and Hawking radiation is completely random, then it seems there is no way for the information to be recovered. This inconsistency led to the suggestion that the information is not just preserved in a subtle form, but that the entire black hole interior is incompatible with the smooth geometry predicted by general relativity. Thus, the hypothesis of the firewall was born. To preserve unitarity, something drastic must occur at the event horizon. The most important consequence of the firewall hypothesis is that it resolves the black hole information paradox in a very dramatic way, by annihilating the information at the event horizon. Instead of preserving the information and releasing it later through Hawking radiation or storing it on the black hole's surface, the firewall hypothesis posits that black holes are ultimate information destroyers. From the standpoint of quantum mechanics, this is a drastic solution, but it also ensures that unitarity is maintained. By destroying the information upon crossing the event horizon, the universe remains predictable and the laws of quantum mechanics remain intact. Information is not lost, but is instead destroyed at the point of no return. For proponents of the firewall hypothesis, this solves the problem of information loss. But this solution comes with significant implications. If black holes destroy information at the event horizon, then no amount of careful observation or computation can ever recover that information, no matter how advanced our technology becomes. The universe itself becomes, in a sense, unknowable once something falls into a black hole. Controversy and debate. The firewall hypothesis has sparked heated debates in the scientific community. While some physicists find the idea of a firewall appealing because it resolves the information paradox, others vehemently disagree with its conclusions. One of the strongest objections is that the firewall idea violates the equivalence principle, which is central to general relativity. If the event horizon is truly a violent boundary, then crossing it would be a radically different experience from what the equivalence principle suggests, which undermines one of the key ideas of general relativity. Moreover, critics of the firewall hypothesis argue that it may be a sign of something deeper and more subtle that we don't yet understand about quantum gravity. Some suggest that the paradox might be a signal that we need a new theory that unifies quantum mechanics and general relativity, such as loop quantum gravity or a fully realized string theory. At the heart of the debate is a simple question. How can we reconcile the smooth space-time of general relativity with the non-local, information-preserving nature of quantum mechanics? If we cannot find a way to reconcile these two theories, then we may need to accept that we are dealing with a phenomenon that requires entirely new physics. Physics that might emerge from a deeper understanding of space and time. What does the firewall mean for the future of physics? The firewall hypothesis challenges not just the nature of black holes, but also the very framework of physics that underpins our understanding of the universe. If the firewall exists, it might suggest that the structure of space-time itself is more complicated than we realize, possibly requiring new models that integrate quantum mechanics and general relativity in a unified framework. The implications of the firewall for our understanding of black holes are far-reaching. If we are correct in our assumptions, the firewall could be a key stepping stone toward unraveling the mystery of quantum gravity, the long-sought theory that seeks to describe the gravitational force on the smallest scales. Chapter 5. The Holographic Principle and Black Hole Complementarity. In the ongoing quest to resolve the Black Hole Information Paradox, two interconnected ideas have gained prominence in recent years: the holographic principle and black hole complementarity. These concepts, which emerge from the fields of string theory and quantum gravity, offer radically different perspectives on how information may be preserved in black holes without violating the laws of physics. Instead of accepting the destructive conclusion of the firewall hypothesis, proponents of these ideas suggest that the solution to the paradox may lie in a deeper, more subtle understanding of space-time and quantum mechanics. In this chapter, we will delve into the intricacies of both the holographic principle and black hole complementarity, exploring how they offer potential resolutions to the black hole information paradox and challenge our conventional ideas of space, time, and reality. The holographic principle, a radical shift in thinking. The holographic principle, first proposed by physicist Gerard Hooft and later refined by Leonard Susskind, suggests that the description of a volume of space can be encoded on its boundary, effectively transforming the space into a hologram. More precisely, the principle implies that all the information contained within a region of space can be described by the information on the boundary of that region, even if that boundary is much lower dimensional. This concept draws an analogy with a hologram, in which a two-dimensional surface encodes a three-dimensional image. The holographic principle arose from the study of black holes, particularly in the context of string theory and ESCFT correspondence, a duality between gravity in higher dimensional spacetime and quantum field theory in lower dimensional spacetime. In the late 1990s, the discovery of ADS-CFT correspondence provided a concrete framework for understanding the holographic principle in the context of black holes. The correspondence showed that a theory of gravity in a higher dimensional spacetime, anti-de Sitter space, or ADS, could be described by a quantum field theory on the boundary of that spacetime. Essentially, this means that the full gravitational dynamics of a black hole in a higher dimensional space could be encoded in a lower dimensional quantum theory without the need for gravity at the boundary. This realization had profound implications for the information paradox. If all the information inside a black hole can be described by a lower dimensional theory on the boundary of the black hole, then information is not truly lost when something falls into a black hole. Instead, it may be stored in some form on the event horizon or in the boundary of spacetime. In other words, the hologram of the black hole's interior exists at its boundary, offering a potential solution to the paradox of information loss. The holographic principle and black hole information. One of the key insights of the holographic principle is that the interior of a black hole, or any region of space for that matter, does not require a detailed description of the bulk geometry, the volume of space. Instead, a lower dimensional theory on the boundary encodes all the necessary information. This idea is similar to how a hologram can represent a 3D image on a 2D surface, and it has important consequences for how we think about the loss of information inside a black hole. According to this principle, the information about an object that falls into a black hole might be stored on the event horizon in a highly scrambled form. Rather than being lost in the black hole, this information would be preserved on the boundary of the black hole's event horizon. This interpretation suggests that the apparent loss of information when matter crosses the event horizon is an illusion, caused by our limited perspective as observers outside the black hole. The holographic principle thus offers a way of reconciling the apparent conflict between quantum mechanics, which demands the preservation of information, and general relativity, which suggests that once information falls into a black hole, it is lost forever. If the information is encoded on the event horizon, the laws of quantum mechanics can be preserved without violating the tenets of relativity. The key idea here is that the information is not lost, but rather becomes part of a broader, higher dimensional description of the universe. In this way, the holographic principle provides a potential resolution to the information paradox. Information is not destroyed inside the black hole, but is instead preserved on its boundary, in a form that we do not yet fully understand. This radical shift in thinking opens up new avenues. Chapter 6. The role of quantum gravity and the search for a unified theory. One of the most profound challenges in modern physics is the search for a unified theory that seamlessly integrates quantum mechanics and general relativity, two theories that describe the universe in fundamentally different ways. Quantum mechanics governs the behavior of the smallest particles of the universe, where probability and uncertainty reign. General relativity, on the other hand, describes the behavior of large objects like stars and planets, where gravity bends the fabric of spacetime. These two theories have been phenomenally successful in their respective domains, but they conflict when applied to extreme environments like the interior of a black hole or the beginning of the universe. In such regions, quantum gravity, the elusive theory that attempts to merge the principles of quantum mechanics with the curvature of spacetime, becomes essential. In this chapter, we will explore the role of quantum gravity in resolving the black hole information paradox. We will discuss the various approaches to quantum gravity, their implications for black hole physics, and how a unified theory could help us better understand the deepest mysteries of the universe. Why do we need quantum gravity? In classical general relativity, black holes are defined by a region of spacetime where gravity is so intense that not even light can escape. The black hole is surrounded by an event horizon, a boundary beyond which no information or matter can return. The singularity, a point of infinite density, lies at the center of the black hole. According to general relativity, this singularity represents a breakdown of space-time itself, a region where the curvature of space-time becomes infinite. However, quantum mechanics tells us that at microscopic scales, things behave probabilistically, not deterministically. Particles are described by wave functions, which encode all possible states the particle could be in. These wave functions evolve according to the Schrödinger equation, which is linear, meaning that information is always preserved in quantum systems. The clash between the deterministic predictions of general relativity and the probabilistic nature of quantum mechanics is what creates the need for quantum gravity. When a massive object collapses into a black hole, quantum mechanical processes are still at play. The behavior of the particles that fall into the black hole, and even the quantum fluctuations near the event horizon, cannot be described by general relativity alone. To fully understand the behavior of a black hole, especially how information behaves when it falls inside, we need a theory that can account for both quantum mechanics and gravity. This is where quantum gravity comes into play. Quantum gravity aims to explain how the force of gravity behaves at quantum scales, especially near extreme gravitational fields like those around black holes or in the early universe. Without quantum gravity, our understanding of space-time breaks down at small scales, and we are left with contradictions that can't be resolved within either framework. Several approaches to quantum gravity have been proposed over the years, each aiming to resolve the incompatibilities between general relativity and quantum mechanics. The most well-known of these are loop quantum gravity, string theory, and the holographic principle. Loop quantum gravity. One of the leading contenders for a theory of quantum gravity is loop quantum gravity. Unlike string theory, which posits the existence of one-dimensional strings as the fundamental building blocks of the universe, loop quantum gravity seeks to quantize space-time itself. In loop quantum gravity, space-time is not a continuous entity, but is instead made up of discrete loops or quantum bits of space. In this framework, space is described by a network of interconnected loops that form a discrete, granular structure at the smallest scales. These loops are akin to the pixels of a digital image, and at the Planck scale, space-time is not smooth, but instead has a granular structure. This discrete structure of space-time implies that there is a fundamental limit to how finely we can probe space, and it suggests that the singularity at the center of a black hole may not be as it appears in classical general relativity. Instead of a point of infinite density, the singularity could be replaced by a quantum bridge or a bounce, where the laws of physics behave differently. In the context of black holes, loop quantum gravity proposes that quantum effects near the event horizon could allow for the preservation of information that falls into a black hole. Rather than information being lost at the singularity, it might be stored in the quantum structure of space-time itself, encoded in the loops that make up the fabric of the black hole. This could mean that the interior of black holes is not a complete mystery, but is instead a region where quantum effects are key to preserving information. String theory and the role of higher dimensions. Another leading approach to quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not point particles but one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to different particles. String theory also predicts the existence of additional spatial dimensions beyond the familiar three. In fact, string theory requires a total of 10 dimensions, 9 of space and 1 of time, although some versions of string theory allow for different configurations of these dimensions. String theory provides a framework in which both gravity and quantum mechanics can coexist. It allows for the unification of the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. In the context of black holes, string theory provides a natural explanation for how information could be preserved. The idea of black hole complementarity, which suggests that information is stored on the event horizon, is compatible with string theory, which allows for the encoding of information in the boundary of a black hole in a higher dimensional space. Moreover, string theory predicts the existence of black brains, multidimensional objects that generalize the concept of black holes to higher dimensions. In these higher dimensional spacetimes, the information paradox might be resolved by suggesting that information is not lost, but instead encoded in the higher dimensional structure of the black hole. This leads to the idea that, rather than information being destroyed, it could be encoded in a way that allows for it to be recovered, similar to how a hologram encodes three-dimensional information on a two-dimensional surface. Chapter 7. The Future of Black Hole Physics. The black hole information paradox is not just an isolated problem in astrophysics. It represents one of the most fundamental conflicts in modern theoretical physics. At its core, it challenges our understanding of gravity, quantum mechanics, and the very nature of reality. Resolving this paradox is not just about understanding black holes better. It could serve as the key to unlocking a long-sought-after theory of quantum gravity, reshape our experimental approaches to studying extreme space-time conditions, and ultimately determine the future of fundamental physics itself. This chapter explores what solving the paradox could mean for physics, whether we have any feasible ways to test these theoretical ideas, and what the future of science might look like if the paradox remains unresolved. One of the most promising prospects of solving the black hole information paradox is that it could lead to a fully realized theory of quantum gravity, a framework that successfully unites Einstein's theory of general relativity with the principles of quantum mechanics. Currently, gravity is the only fundamental force of nature that lacks a quantum description, while electromagnetism, the strong nuclear force, and the weak nuclear force all operate within the well-established framework of quantum field theory. Gravity remains resistant to quantization. Black holes, where both quantum effects and gravity play an equally dominant role, provide a natural laboratory to study this unresolved tension. How could solving the paradox lead to quantum gravity? 1. Clarifying the role of space-time at the quantum level. If black hole information is preserved, it means that the classical description of space-time must be modified at microscopic scales. Any resolution to the paradox must explain how quantum information interacts with space-time without violating the principles of either general relativity or quantum mechanics. This could lead to new insights into the structure of space-time itself, possibly even suggesting that space and time are emergent properties of more fundamental quantum processes. 2. Identifying new principles for a unified theory. Several proposals for solving the paradox, such as holography and entanglement-based reconstructions of spacetime, suggest that information conservation is a deeper principle than previously realized. If true, this could point toward an entirely new way of formulating physics, one where gravity is not a fundamental force, but an emergent phenomenon arising from underlying quantum information dynamics. 3. Guiding the development of quantum gravity theories. Leading candidates for a theory of quantum gravity, such as string theory and loop quantum gravity, offer different perspectives on how black holes should behave. A clear resolution to the information paradox could provide crucial constraints on these theories, helping physicists determine which approach, or combination of approaches, is correct. If we succeed in constructing a quantum theory of gravity, it will not only resolve the mysteries surrounding black holes, but could also offer answers to long-standing questions about the nature of the early universe, the fate of singularities, and the fundamental structure of reality itself. Can we test these ideas? While theoretical advances have brought us closer to understanding the paradox, any scientific theory must ultimately be tested against empirical observations. Given the extreme nature of black holes, testing these ideas is a formidable challenge, but not an impossible one. 1. Gravitational wave observations. The detection of gravitational waves from black hole mergers has already provided unprecedented insights into black hole dynamics. Future gravitational wave observatories, such as LISA, laser interferometer space antenna, could detect subtle deviations from classical predictions, possibly revealing quantum corrections near the event horizon. If modifications predicted by quantum gravity models appear in the data, they could provide strong evidence for a resolution to the paradox. High-resolution black hole imaging. The Event Horizon Telescope, EHT, has already produced direct images of black hole shadows. Upcoming advancements in radio astronomy could allow us to detect small deviations from classical general relativity predictions, such as the presence of quantum hair on black holes or evidence of information leakage through exotic mechanisms. If black holes are not completely smooth and featureless, as Einstein's equations suggest, but instead possess a complex structure encoding information, high-resolution imaging might reveal it. But 3. Analog black hole experiments. Some condensed matter systems can mimic the properties of black holes, particularly in the study of Hawking radiation. Experimental setups using Bose-Einstein condensates and other quantum fluids have already demonstrated effects analogous to Hawking radiation. If these laboratory analogues show deviations from purely thermal radiation, it might provide indirect evidence that real black holes also preserve information. 4. Quantum information and computational simulations. Quantum computing could play a crucial role in simulating black hole information dynamics. Recent breakthroughs in quantum entanglement research have suggested that quantum computers may be able to simulate black hole behavior in ways classical computers cannot. If these simulations reveal mechanisms by which information escapes black holes, they could provide theoretical confirmation of certain resolutions to the paradox before direct observational evidence is available. While these methods are still in their early stages, they demonstrate that testing black hole physics is not an unreachable goal. As our observational and experimental tools improve, we may finally be able to determine how black holes handle information and whether quantum gravity can be experimentally verified. What if the paradox remains unresolved? While physicists remain hopeful that a resolution will emerge, there is a possibility that the information paradox may persist as an unsolved problem for decades, or even forever. If that happens, what would it mean for the future of physics? If black hole information loss remains unresolved, it would imply that there is something fundamentally incomplete about our current understanding of nature. It could suggest that either quantum mechanics or general relativity, or both, require radical modifications that we have yet to conceive. A failure to solve the paradox might signal that our theoretical frameworks are insufficient for describing the true nature of the universe. The inability to resolve the paradox might indicate that entirely new principles beyond our current understanding are required. Some physicists argue that information conservation might not be a fundamental law, but instead an emergent property under certain conditions. If this turns out to be the case, our understanding of reality might need a complete reformulation, potentially leading to a new era of physics. If the paradox remains unresolved, it might not be due to a lack of theoretical progress, but rather the inherent limitations of observation. Since black holes are incredibly difficult to study directly, the key to solving the paradox might remain out of reach, simply because we lack the technological means to gather the necessary evidence. Future advancements in observational tools, perhaps even technologies that do not yet exist, might be required before we can definitively answer this question. If no clear solution to the paradox emerges, some scientists might turn away from traditional physics approaches and explore more radical ideas about the nature of information and reality. Some speculative theories suggest that space-time itself may be an emergent phenomenon, and that black hole paradoxes arise because we are looking at the problem from an incomplete perspective. If true, this would indicate that the real resolution lies not just in understanding black holes, but in redefining the very nature of what we consider fundamental physics. The future of black hole physics is intertwined with the search for a deeper understanding of the universe. If we solve the paradox, we may finally unlock the secrets of quantum gravity and gain insights into the fundamental structure of space-time. If we fail, we may be forced to rethink our most cherished theories and develop entirely new frameworks for understanding nature. Regardless of the outcome, the pursuit of answers to the black hole information paradox will continue to drive theoretical physics forward, pushing the boundaries of knowledge and reshaping our understanding of the cosmos. As new technologies emerge and experimental capabilities improve, the day may come when we finally uncover the truth about black holes, information, and the ultimate fate of the universe.